Our first interesting electronic component is the resistor. A resistor follows the constitutive equation for Ohm's law, which is V equals IR. The voltage across the resistor is equal to the current through it times its resistance. Our resistors came on a reel of tape, and if you want to remove it, you just rip one out. You have a whole baggie of a bunch of different values. Let's talk about how we figure out what the value is. Okay, so this one is a color band of brown, black, red, and gold. So a color like gold will always go on the right, and then we'll have three colors from left to right that represent the value of this resistor. And I'll let you find online a little calculator or a cheat sheet for how to read this. But brown, black, red, gold means that this is a 1K resistor. So brown, black, red, gold. Means that this is a 1, 0 times 10 to the 2 ohms, which is a 1K ohm resistor. The gold part is a specification that says this is a plus or minus 5% resistor. Now, if you were to take all of your 1K resistors and read them, they'd be well within 5% of each other. This 5% is now more related to, does this hold up to 1K over the temperature range that it's specified for? So at 0 degrees C and 100 degrees C, is this still a 1K resistor, or does it change by as much as 5%? And you could buy more highly specified resistors. These are just kind of like the very basic ones. What I like to do sometimes is, after you figured out the value of your resistor and there's still a lot on your piece of tape, go and write on your piece of tape that this is the 1K. Make them a lot easier to find in your bag later. These resistors cost about, 0.4 cents. So after you're done with it, feel free to throw it away. You have plenty to get through this course. Maybe don't throw it away if it's still in nice condition like this, but eventually you'll bend it and you'll cut it, and eventually the wires will get so small it's not usable. Don't worry about saving these. If you need more, come to the mechatronics lab and feel free to restock your kit. So how do we use a resistor with our breadboard and end scope? Well, we'll take our hands and we'll just bend the wires, kind of in a perpendicular U shape, and now I can stick it into the breadboard. Okay, first lesson. Why is this not an appropriate way to plug into the breadboard? Both legs of the resistor are in the same row. Well, we know that the row of the breadboard is one piece of wire, so this is essentially taking my resistor and connecting the two ends. How do I draw that as a schematic? Well, our resistor is kind of a zigzag line. That's our circuit schematic for a resistor. Usually we would label it, so this is a 1K resistor. And by the way I've plugged it into this breadboard, I've essentially taken one leg and attached it to the other leg because they're both in the same row. If both legs are connected with a wire, and a wire has 0 ohms of resistance, both sides have to be the same voltage because of V equals IR, where the R is 0. This is not a very interesting circuit. It can't ever do anything. If you ever see a component like a resistor with both legs in the same row, it's not doing anything. It might as well not even be there. So don't plug anything in where both legs are in the same row. So instead, we should be plugging it in with each leg in a different row. Okay, how do we get some current to go through this resistor? Well, we have to put a voltage across it. So if I were to take 5 volts across this resistor, which is a 1K, I would get 5 milliamps of current. So let's do that. On the right side of my end scope, I have a 5-volt rail and a ground rail. So the column of holes by the red stripe, all of those are 5 volts. And then the column of holes next to the green stripe, those are all ground. And of course, we actually have another ground on the left and a -5 on the left as well. So we have 10 volts to play with if we wanted. But let's stick with 5 volts and ground. So one way to make current go through this resistor is just take one leg and put it in 5 volts and the other in ground. Note that because these columns are all connected, I don't have to put them in the same row, although I could. It's a little tight to fit in there. So right now I have 5 milliamps going through that resistor, or it's a little easier just to spread them out like that. Okay, so 5 milliamps going through that resistor. What if I didn't want to plug directly into the rails, if I wanted to use the breadboard space? Now I need to use some wires, so I'll use a red wire and a black wire. We like to use red for power and black for ground. So I'll connect one leg of the resistor to 5 volts, the other end to ground. Okay, now once again there should be 5 milliamps going through this LED. And note that I didn't have to build in this configuration. I could have gone this way. That is, conveniently on the same row. It doesn't have to be in the same row. Could look like that. Could have been way down here. Could have been, way up here. We don't want to go inside of this space because that's where channel 1 and the outputs are. So we're going to stay kind of below the bottom side of the end scope. Now I keep saying I've put 5 volts across this resistor and there must be 5 milliamps going through it. How do I know? Let's not use the end scope just yet. Let's look at our multimeter. So on the multimeter, first we're going to turn it on. And I want to know what's the voltage across this resistor. So I'm going to go to the DC voltage setting. And I know it should be 5, so I need to go above the 2 volt setting because that would have a maximum voltage of 2. So I'm going to go to the 20 volt setting. And I'm going to put my black lead on the negative or the ground side of the resistor, and then my red on the positive, and I get 4.95, so almost 5 volts, which is, this is basically 5 volts. Okay, and then in my head I can just do the math. 5 volts divided by 1K is 5 milliamps. How do I get the current? Well, if I just went to the current setting of my multimeter, and in this particular multimeter, if I want milliamps of current, I would go to the milliamps hole, and amps of current, I would go to the amp hole. So don't do this, just follow along for a second. I'm going to go to the amp hole, and I will go to the DC amps. I'm going to read as much as 20 amps. And if I was like, oh, how do I read the current through this resistor? I'll just touch either end like I did with voltage. Well, it spiked, and then the end scope turned itself off. Because what did I do? I just added a very low resistance path for the current to go around the resistor through my multimeter to ground. It drew more than 100 milliamps, so the end scope turned itself off for safety. And hopefully we didn't blow the fuse on our multimeter. That's why I went to the 20 amp setting and not maybe the 200 milliamp setting because I might accidentally blow that fuse. Okay, so how do we read current? First I'm going to turn my power back on. And let's go to the 20 milliamp setting. And I'm going to move my probe to the milliamp hole. Okay, so now I should be able to read current. If I want to read current through this resistor, I have to break open the circuit to be able to have the current go from this red wire through the resistor through my multimeter to ground. So I'm going to pull open the black wire. It's not plugged into anything now. I'm going to touch the red probe to the leg of the resistor and the black probe to the black wire. And now I can see I've got almost 5 milliamps through this resistor. As soon as I let go, of course, now no current can flow anymore because the circuit's broken open. So remember, to read voltage, you can read directly across. To read current, you have to break open your circuit and then insert your multimeter as if it were a component to force that current to go through the multimeter to get a good reading. And note that if I put them backwards, I just got my sign convention wrong, so I'm seeing negative. Okay, how do we make more interesting volts than just 5 volts? Well, we can make a voltage divider. We'll have a whole video on that soon. But I'm, for now, just going to have another 1K resistor in series with this 1K resistor. And it will go to ground. So, again, if I want to read with my multimeter, I'll go to the 20 volt setting, and from ground to power I should have 5 volts. Remember, you have to move to the volt hole. So ground to power, I have my 5 volts. What if I want to know the voltage across this resistor? I can touch either end, and the voltage across this resistor, touch either end. And if I got it backwards, I should see the negative voltage. And if I wanted to know the current, I will break open my circuit so that no current can flow. And I have to switch back to milliamps. I wonder how much I'm going to get now. I used to get 5 milliamps. Now I have 2. I'm going to guess half, because I've got twice the resistance. I also saw that I had 2.4 volts across each of these resistors, so they must have 2.4 milliamps, and here we go, 2.46 milliamps. Okay, we know Ohm's law, so we know V equals IR. That's fun to play with. The last thing we might be interested in is power. What is the resistor doing? Well, it's resisting the flow of that current, and it's turning it into heat. So power has the units of watts, and is the current through something times the voltage across it. And we could use Ohm's law here so that the power dissipated by a resistor is I squared R, and it's also V squared over R. So if we know the current through the resistor and its resistance, we know how much power it's dissipating. And if we know the voltage across it and its resistance, we know how much power it's dissipating. Now, what does that mean? That's turned into heat. So these little resistors right now, when I connect them back in series, so now current's flowing again, they're heating up a little. And because they've got some surface area, they're conducting that heat, convecting that heat into the air. At some point, though, it can't convect as much heat away, and the temperature starts to rise and rise and rise. And what happens when something's temperature rises forever? It eventually will burn up. So that's why one thing we have on the end scope is if you draw over 100 milliamps, it will turn itself off. Hopefully that saves a lot of your components. But also you want to think before you're using a resistor or something that acts like a resistor, maybe a motor, what is its resistance? And if it's going to behave like a resistor, how much power will dissipate and how much heat can the surface area of your component dissipate before it catches on fire?